thing with density here, while we're still on the topic, is that using density, you can pretty readily convert masses into volumes and volumes into masses. And this has a lot more utility than you might think. My wife was doing some recipes here recently, and they were recipes from Europe. And in Europe, they measure a lot of times things in grams, but of course she had things with cups and teaspoons and stuff, and those are volumes. So Europe apparently has a lot more recipe masses, grams and stuff like that, while America uses a lot more volumes, and that's fine, just one of those things. But anyway, if you ever need to, the density will allow you to go from a mass to a volume. So you can translate the European values to American quote-unquote values, or vice versa and stuff. This introduces also something which we'll use a lot in Chem 220 series, which has different names to it: dimensional analysis or factor label. And what those terms mean really is that you're starting with one unit and you're converting to another kind of unit. And in the process, you have to take the old unit and quote-unquote cancel it out. So if you start with, earlier we saw millimeters and you wanted to go to centimeters, you have to cancel those millimeters out. And to do that, you put a millimeter in the numerator top and a millimeter in the bottom denominator. Millimeters over millimeters are equal to 1, so they cancel out, quote-unquote. That's really what this stuff is all about. This is all stuff that you do a lot in your day-to-day world. If you want to convert $1 to $10, or if you have 20 quarters and you want to know how many dollars they are, all right? These are the kind of things that we do a lot of times don't even think about. But when it gets the fancy names, I know it can be a little weird. But just remember, it's like you're starting with something and you want some kind of desired unit. And in order to go from A to B, you've got to cancel A out. And you do that by having the unit in the top and the unit in the bottom, all right? So we're going to talk about this a lot, and we'll talk about this on Wednesday too during our recitation a little bit. This is a problem which is more chemistry based, all right? We have 95 milliliters of mercury. A can, 12-ounce can of pop is, I think, 355, something like that, milliliters. So that gives you a rough sense then what it is. This is much less than one can, if you will, of mercury. Anyway, we want to convert the 95 milliliters into a mass. And I have up here both grams and pounds. A pound in the United States is about 454 grams in the metric system. And we also have here the density of mercury. Now remember, density is mass per unit volume. So in a centimeter cubed of volume, which is like a milliliter, you're going to have 13.6 grams or mass of mercury. And we can use all this information to turn our volume into a mass. Now, along the way, as I talked about earlier, a milliliter and a centimeter cubed are the same thing. So if you wanted to write this as 13.6 grams per milliliter and use this milliliters, awesome. On the other hand, you're like, boy, I want to be cool. I want to have centimeters cubed because it looks kind of cool, I think. Anyway, cool, no problem. Cut out the milliliter and call it centimeters cubed, then you'll have a centimeters cubed there and a centimeters cubed there. They are literally interchangeable, milliliter and centimeters cubed. So, without further ado then, let's see how you would convert the 95 milliliters into a mass of grams or pounds. And again, the important thing, centimeter cubed and a milliliter, same thing, all right? If you want to call one the other and the other the same, that's fine. They really are the same thing. Centimeters cubed is really useful if you have a solid, because length times width times height, we talked about earlier, is one way to measure a centimeter cubed. On the other hand, milliliters, which you pour, are oftentimes done with milliliters because it's easier than to see their volumes. So solids almost always will be centimeters cubed and liquids will almost always be milliliters, but you can interchange them, all right? Dare to be different, yeah. It's totally fine, whatever you want to do. So anyway, 95 centimeters is the same as 95 milliliters, 1 to 1. And if we want to turn the volume, centimeters cubed or milliliters, into a mass, which is grams at first, let's use the density. And we do this because this is a way to convert from a volume to a mass, from centimeters cubed into grams. We want a mass. Grams is the first stop. So if we want mass in grams, we start with a centimeter cubed. We've got to have something where centimeters cubed are on the bottom. This centimeter cubed and this centimeter cubed will cancel, just like 4 over 4 equals 1. Centimeter cubed over centimeter cubed equals 1 as well. The units will cancel out in my world. And the only unit left standing, the only units that are left, are going to be grams. So in your calculator, 95 times 13.6 will give you a number. It may look a little bit different than that. Again, I'm going to talk about significant figures here in a little bit. But 1,300 grams is the answer I have right there. I wrote it in scientific notation because numbers that are big and small are easy to do it. You could also write this out as 1300, and that would be fine. So again, I will talk about why this number may look a little different than your number on the calculator here in just a little bit. If you want the mass in pounds, it's not hard. In this problem now, we're starting with grams, and we want to go to pounds. So we're going to need a conversion to cancel out the grams. That's going to be this thing right here. And if you put the 454 grams on the bottom, you can see how now you have grams on the top and grams on the bottom. They cancel out. Pounds, which has the symbol LB, is the only unit left standing. And again, to 2 sig figs, 2.9 pounds. Okay? Any questions? Okay. This is a graphic description of what exactly this centimeter cube thing is all about. So literally a centimeter cube, length, width, and height are literally just equal to a centimeter. And again, like I said, a centimeter cubed and a milliliter are the same. Now, a lot of times in physics and engineering, instead of centimeters cubed, they'll use meters cubed, which are fine. And a meter cubed is the same idea. Length, width, and height are all equal to a meter. If you took one of the little blocks there from the meter cubed, you would have what's called a decimeter cubed. A decimeter cubed, a deci is another metric prefix. It's not one of the ones I want you to know, but if you hear it, that's what it is. Decimeter is decimeter times decimeter times decimeter. A decimeter cubed technically is the same as a liter, but I don't know anybody that uses that. And then one of the small little blocks from that is what a centimeter cubed is. Now, why chemists use centimeters cubed, and liters for that matter, a lot, is these are real convenient units to use, all right? Like a liter of pop at the store, all right? And you can have many, many milliliters or centimeters cubed in a kind of a thing. But it totally depends on the type of application you're using. Again, a lot of times in physics and engineering, they won't need to have milliliters and liters so much, so they'll use meters cubed, and that's totally fine. It just depends on the field you're in and what you're having to use. I'm a big fan of the Marvel movies, Doctor Strange, and this is him trying to figure out gallon, pint, quart, cup, teaspoon, et cetera, and all the different units around. And this is how I feel when I have to use the empirical things. You can see how in metrics, it's like, this is one of the little cubes, and this is one of the cubes from there, and blah, blah, blah. I can figure out that part pretty easy, but man, the other ones, I'm always like trying to do magic spells, and my magic wand doesn't work very well in the empirical units, but anyway, I digress once again, as always. Questions? My goodness, it's getting hot in here. No, seriously, temperature is another important scale when it comes to chemistry. And in the old days, Fahrenheit tried to figure out the absolute coldest temperature possible and what he thought was the hottest temperature, and the Fahrenheit scale was born. Now in Fahrenheit scale, which is what I grew up in good old Gresham, Oregon, USA, 32 is the freezing point and 212 is the boiling point of water. And in my mind, I use those unfortunately quite a bit because that's what, you know, the TV will report for what the temperature is going to be tomorrow. They're usually Fahrenheits, and that's fine. However, in the chemistry world, we almost exclusively use Celsius and the Kelvin scale. Now Celsius came along and he made a scale where 0 Celsius was where water froze and 100 Celsius was where water boiled. Again, note that 100 gap, that's a power of 10. And using that is really, really cool. Celsius's scale is what we use almost always in lab. So next week when we do the density lab, we'll do some recordings of temperature in Celsius. And it's easy, you have a thermometer, all right? But instead of reading Fahrenheit, like maybe you've used before, this is just a Celsius thermometer. Works really, really well. When you get to theoretical studies though, it's nice to know the point where matter stops. Now earlier when I had the 3 of you on the stairs being solids, even as a solid, you were moving around like a little bit, okay? At 0 Kelvin, even that stops. All right, you're literally, there's nothing else happening. 0 Kelvin is supposedly the point where all motion stops. You literally have sucked the energy out of it, you know, and it's kind of crazy. It's called absolute zero. And for our classes, Chem 221 through Chem 223, we're going to say that's the coldest temperature possible. Now, prof hat off. There are studies being done. They think they can go below 0 Kelvin, which is, wow, blowing my mind. But prof hat back on. Most of the time, we think of 0 Kelvin as being the absolute scale, the absolute coldest it can go. And that's where the Kelvin scale comes in. 0 Kelvin is that absolute 0 point. That's the point where all the motion stops, even the motion of solids, all right? And it's easy to go from Kelvin to Celsius. There's a 273 number. I'll show you here in a little bit. Celsius temperatures can be positive or negative. In our class, Kelvin temperatures will be never negative. And when we're making calculations on energy and stuff like that, Kelvin temperatures will be used, and you shouldn't get negative Kelvin temperatures. If you do get a negative Kelvin, something's wrong with the math. It's a nice way to kind of check yourself. So again, Celsius we'll use in the lab, Kelvin we'll use for calculations, but gosh darn it, all the radio stations, TV stations, and even my app record the temperature in Fahrenheit, so we have to know at least a little bit how to go back and forth. We're mostly going to use these two, but a little bit in that. Here's a scale, again, showing what's happening. Fahrenheit, 32 to 212, a difference of 180 degrees. But notice here how Celsius and Kelvin scales are set up. So first of all, freezing point of water in Celsius is 0 and boiling is 100. So the gap between those two is 100 degrees, which is really nice. Now, 273.15 is the Kelvin freezing point of water, and 373.15 is the boiling point of water. So notice that the difference between freezing and boiling in Kelvin is the same as the difference between the boiling and freezing in Celsius. And believe it or not, that is super cool for chemistry, because we'll talk about, a lot of times, just like we talked about a change in volume earlier, we'll have lots of changes in temperature. And a change of temperature in Celsius will equal the change of temperature in Kelvin. Woohoo! So that's pretty cool. We're going to see that has a lot of neat uses. However, if you only have a Fahrenheit temperature, you're going to have to convert your change in temperature in Fahrenheit into one of these because that gap is different. So again, try to stay away from Fahrenheit as a chemist if you can. It just makes your life easier. You'll be able to translate it easier, but you can translate from one to the same if you need to. Another thing about Kelvin, and this is now where, of all things, astronomers and sometimes photographers versus chemists get into some arguments. Technically, Kelvin, all right, doesn't have a degree symbol, all right? Fahrenheit and Celsius do, but Kelvin does not. And both astronomy and photography sometimes, they'll use degree
degrees Kelvin.
And in my world, that's like saying, you ain't knowing what's going on. Like, you know what I'm saying, but ain't isn't really like an official word. So, you know, SMH, those kind of things. Anyway, all right, it's nice to do it officially. And so officially, Kelvin doesn't use a degree. So try to not use degrees when it comes to Kelvin. If you do, it's okay. And also, in our classes, we won't have negative Kelvin temperatures. I'm not going to say you won't see them outside of my chemistry classes, but in our classes, Kelvin shouldn't be negative numbers. Cool? All right. Foxtrot, again, you know, recipe says to bake the cookies in a 350-degree oven for 14 minutes, and he doesn't know if it's Fahrenheit or Celsius or Kelvin. And of course, probably because US of A, it's Fahrenheit, and that makes sense, you know, but you never know. And then then this guy brings up, well, maybe they want you to rotate the oven just shy of a full circle, because a circle is 360 degrees, which is something totally different. And he goes, oh, don't be ridiculous, you know. But really, these are good things. You have to have the unit with the number, or else technically you don't know if it's Kelvin, Fahrenheit, Celsius, or just sort of a full circle. I have a strange sense of humor. Questions on any of that? All right. When you go from Celsius to Kelvin and Kelvin to Celsius, it's pretty chill. Now remember, Celsius numbers can be negative. Kelvin temperatures in our classes will never be negative. So if you have a Celsius, add 273.15 to it to make the Kelvin temperature. If you're going from Kelvin to Celsius, you would just put the 273.15 on the other side, and you would subtract 273.15 from it. So again, it's pretty easy, but remember in the back of your mind, Kelvin's always positive. The body temperature, the temperature of your body is about 37 degrees Celsius, give or take. If we wanted to convert this into Kelvin, you would add 273. Now, for this problem, I'm cutting it off after the 3, and there's a reason for it. I'll talk about that later. But when you do this, you get 310 Kelvin. Also notice I put a dot by the 0. Sig figs are coming out here, and all of these things are about sig figs. So I'm just kind of throwing them up there. We'll talk about what they mean here in a little bit. But the important part is that for right now, if your body's 37 degrees Celsius, that means your body has a temperature of 310 Kelvin. Okay? You just add 273 to it, or 273.15. Now, liquid nitrogen is one of the colder substances known. Liquid nitrogen has a temperature of 77 Kelvin. So if you're curious what Celsius that is, you would subtract 273 from it, and you would get minus 196 degrees Celsius. Now remembering that 0 degrees Celsius is where water freezes, this is pretty cold. Don't put your fingers in the liquid nitrogen. Terminator 2, another good movie reference. That was liquid nitrogen, supposedly freezing him there at the end and stuff, and he was... Okay. You don't have to like any of these movies to do well in my class, by the way. I'm just pointing them out. So. Okay. Crazy Fahrenheit. All right. Once in a while, it's nice to be able to convert Celsius to Fahrenheit or Fahrenheit to Celsius. I like to make connections to your real world, to this class. All right, it's not just academic, dreams and stuff like that. The temperature conversion is a little weird. Fahrenheit equals 9/5 times the Celsius plus 32. Sometimes you'll see 1.8 there instead, and that's fine as well. All right, so either 1.8 or 9/5 times the Celsius temperature plus 32. Liquid helium is a substance which is even colder than liquid nitrogen. Liquid helium has a temperature of 4.2 Kelvin. And if I said, what's the Fahrenheit temperature of liquid helium? What I would do is I would first convert Kelvin into Celsius, because then you can use this equation. So Kelvin minus 273.15, you get minus 269.0 degrees Celsius, also cold. And this is the number you put in right here for the T of C. So 9/5 or 1.8 times the Celsius plus 32, Fahrenheit minus 452.1 Fahrenheit. Pretty freaking cold. Liquid helium. Anyway, sound effects not necessary. Questions? Here's a kind of a question you might see. These are all temperatures on the Earth. 29 Celsius, 45 Fahrenheit, 256 Kelvin. And it says put them in order of increasing temperature. Now Celsius is kind of like the midpoint of all of these. Like you can go Fahrenheit to Celsius pretty easy, and you can go Kelvin to Celsius relatively easy. So what I would do here is I would convert both the Fahrenheit and the Kelvin to Celsius and go from there. Now, it was 273 Kelvin to convert Kelvin to Celsius. This is going to be a temperature which is less than 29. All right, so we know that this temperature is less than 29. 273 Kelvin would be 0 Celsius. So this is a number less than that. That means it's going to be a negative number. This is the trickier one to convert because 45 Fahrenheit, that would equal 9/5 times the Celsius plus 32. So we would subtract 32 to divide by 1.8, stuff like that. When you do this, this is what you end up with. The 256 Kelvin is the coldest. The 45 Celsius is in between, and 45 Fahrenheit, is in between, and 29 Celsius is the warmest. But again, the key part here is that I would recommend converting Kelvin to Celsius and Fahrenheit to Celsius. It's kind of like the midpoint of those three. Any questions? When you measure things, the units, of course, are really important. And depending on what you're measuring, you'll have different kinds of units. So lengths you've seen in this class so far are oftentimes done in mass, all right? Or meters, thanks for playing. I was making sure you're awake there, that's all. No. Length is usually in meters, and that includes centimeters, millimeters, stuff like that. Mass is usually in grams or kilograms, and time is usually in seconds. Now, scientists got together and they created a set of units called SI units. And SI is a French expression, it's System International, so International System of Units, basically. And the SI units are very handy, as we'll see, for future discussions. So the SI unit for length is the meter, but the reason I have kilogram here is the SI unit of mass is actually the kilogram. In chemistry, we use grams more than kilograms, but the kilograms are important. Time would be seconds. And the SI units can be pretty handy. Now, not all measurements, though, need units. Qualitative measurements are, what's the quality of the substance? What color is it? Is it a solid or a liquid? Is it like chunky? Does it make a color? These are the kind of things that would be those kind of measurements. Those are more, I guess, descriptive. The quantitative ones, which are quantity, those are the ones that need the units. And most of the time we worry more about the quantitative ones than the qualitative, but the qualitative comes in really handy as well. In addition to qualitative and quantitative, depending on the type of measurements you take, you have to think about accuracy and precision. Now, I'm going to step out on a limb here a little bit, but right now with all the vaccine information, all right, there's some people that think they have some information on vaccines, and some can argue for it more accurately or not than the others. But people have to think about the accuracy and precision of measurements as much as anything. And if you're going to do something important like a vaccine efficacy, you have to take many, many measurements and average them over time. So let me share with you an example, using a silly example of a dartboard, all right? And if you've ever played darts before, in the dart you usually throw like 3 at a time. The goal is to get the blue center, and of course the closer to the blue, the better. Sometimes the big things have different points to them, all right? In this problem, we're gonna assume that blue is an accurate measurement, all right? So I hit the blue and I did a good job with my measurement. On the other hand, the farther I get from the blue, then I'm less accurate. But there's also something called precision. I want to be able to throw in the same way each time, all right? And if I'm focused, I would probably do a good job. My 3 measurements would be very close to each other. So this is a good example of how precision and accuracy come together. So bear with me just for a second. So let's say, woohoo, first lecture done today, and I go across the hallway to Gino's if I'm 21 and over, and they actually have a dart machine over there. And so I said, all right, first lecture over, I'm gonna go throw darts. And oh, look at that good throw. Oh, a second good throw. And oh, beautiful. This first throw of my darts, I would consider to be both accurate and precise. I did a good job getting it where I wanted to. I got the actual value. I got the desired value, the blue one. So that's accurate. But also, notice how the 3 darts are really close together. That means I have good precision, repeatability, all right? I'm not just some kind of one-off, kind of a random kind of thing. I've done a good job. I can repeat my data. I would call this both accurate and precise. And this is what scientists want to do when they do a measurement. They want to not only get the right answer, but they want to have something that's repeatable, all right? You don't want to have just one experiment saying something crazy. You want to be able to do it more than once. That shows then that you've got a good technique, okay? So accurate and precise, really important. However, now I've had a couple of root beers at Gino's, and because I'm so excited, and oh, I'm throwing, oh, look, I'm not pretty, oh, see, I'm not doing very good, oh. I wasn't very accurate on this one, all right? I was a little caffeinated or sugared up or something like that. However, notice here how all 3 of my darts were very close to each other, all right? That means that I'm not very accurate, but I am very precise. I still had a good technique, I just wasn't aiming quite right. In science, this happens actually quite a bit. I've got great technique, and I'm able to get repeatable data, but I don't know how accurate I was. So this particular type of throw here, I would consider to be very precise. My measurements were repeatable and they kept happening, but they really weren't very accurate. Something was wrong in this case with my throw. I was too sugared up, I was too caffeinated, whatever. This happens a lot in science, all right? You'll have some great idea, and man, you'll get repeating after repeating an experiment, which is good, high precision. But sometimes that doesn't necessarily mean you have high accuracy. To get accurate results, you usually need some kind of an outside way to see if you're right or not, all right? Like I can say, oh yeah, that's right, the sky is red. And if I go out 3 times in the early morning, maybe it would be red. But of course, most of the time the sky is blue. So you have to be very careful as a scientist that you want to have high precision, but you also want to have high accuracy. Now, finally, after I've had now a few too many Diet Cokes or whatever, root beers, whatever, and I throw my darts, oh, geez, look at this. I can't even keep my values together. All right, I'm way too sugared up or something like that and freaked out. This would be an example of not having good precision. I'm not doing a good job repeating my data. And also, it's not accurate at all. I'm not even close really to the center, like maybe the average of the 3 or something like that. So why I bring this silly dartboard up is because as a scientist, you've got to be always thinking about your precision and about your accuracy. And the first thing to always shoot for is precision. You want to have good technique. You want to have a repeatable value over and over. If you have, say, a measurement, and the first time you use 31 milliliters of HCl, and the second time you use 32 milliliters of HCl, but the third time you use like 50 milliliters of HCl, well, probably the first 2 then would be considered better precision, and that third one's an outliner, all right? And this happens in science. This isn't anything about being a bad scientist. It just means that it happens. You get distracted, you've got bad chemicals, I mean, who knows what. But even if your 3 measurements, 30 milliliters, 31 milliliters, 32 milliliters, even if they have high precision, maybe there was a flaw in the initial experiment. So we have high precision, the numbers are close, but it actually shouldn't have taken that much because I did something wrong in the beginning. One time I did a lab and I accidentally added too much acid. And so I got a lower value than I shouldn't have had, but it was very repeatable because I kept repeating the mistake all the time. So as a scientist, these are the things that we think about, all right? You want to have high accuracy and high precision. Now, usually, all right, in the labs we're going to do, if you have high precision, your values are repeatable, close to each other, that usually means for us that that's high accuracy. In the real world, you want to be a little bit more careful with that because not necessarily. Sometimes you can have different amounts. Questions on that? This is just a stupid ad I saw. You don't want to stand too close to the dartboard, especially with poor precision, because poor precision would mean your values are all over the place. And so this ding dong is standing right there, right in his neck or something, right? I have a very strange sense of humor, so don't throw darts and drink pop, kids. Okay, so accuracy is something that can be measured in lab, and we'll do this later on this term. Accuracy is usually, for us anyway, measured in what's called a percent error. So we have some kind of external way to know what the actual value is, and comparing our value to the actual value, you end up with something called a percent error. And it's just a number, and the smaller the value, usually the better. On the other hand, precision, i.e. how close the results are to each other, can be measured in something called a parts per thousand. And parts per thousand is just a way. Smaller parts per thousand means more precision. Bigger parts per thousand means less precision. So later on in lab, we'll do both percent error and parts per thousand. Remember back to the slide, and that's what we're measuring. We're measuring how close your values are to each other, the precision, and then percent error means how accurate you are too. We're going to buzz through this pretty fast. Parts per thousand and percent errors have these equations right here. These are things that we'll use later. But again, both of these give just a number. Parts per thousand is just a number without units. This is actually a percentage because it's based on 100%. We will use all these things later. In some of the math classes, they use standard deviation, which is another way that's used to measure precision. And that's a cool thing too, but we're not going to use it in our class. But that is another way that you can measure these kind of things too. Okay. And here's an example. I don't feel like going through it, but if you're curious, this is what you can do to see it. But again, we'll do more of this in lab later. All right. The thing I really want to talk about here before we go is the significant figure concept. And because there's so much measurement in my world, all right, we have to have a way to bring all these measurements under control. A calculator, if you say figure out what pi is, it goes on for thousands and thousands and thousands of digits. And you don't want to have to use all those digits every time you use pi. So you find the area of a circle, you don't have to use all the gazillion values of pi. You maybe just want to use 3.14. And significant figures are a way that chemists get their measurements under control. So you don't have to spend a lot of time typing in lots of numbers on a calculator. You can only use the ones which are legitimate. Every measurement we take is going to have some uncertainty to it. And what that means, if I said, hey, let's figure out this volume, there's going to be a plus or minus with each one of us in this room. So let's say, for example, we wanted to measure this number, and you look at the graduated cylinder. These are milliliters, so 15, 16, 17, 18, 19, 20. This would be 17 milliliters. So I think we can all agree here that it's more than 17 milliliters and less than 18 milliliters. 18 would be up here, 17 would be right there. By the way, you usually measure from the bottom of this curve called the meniscus. So if you measure from the bottom here, more than 17 and less than 18. But the question is, how much more? 17.5, 17.4, 17.45, 17.455. I mean, where do we go? Do we just call it 17? And these are the things that chemists have to think about all the time. And if you don't think about them, it drives you crazy. No, seriously, it can be really frustrating because at the worst case scenario, you'll get inaccurate results. And the best case, you might end up with having to put a gazillion digits in your calculator. And you don't need to do that all the time. So knowing how much to measure and how much to report is a huge part of chemistry. So in chemistry, we use this system called significant figures, sig figs for short. And that's probably the most important topic from this first section, chapter 1. all right? We use it all the time from Chem 221 up to Chem 223. And it's just a way to get our numbers all together, get them important. If there's one thing I can ask you to focus on this first week is try and read up on sig figs, all right? Figure out what they are, figure out how to use them and stuff like that. It will make a big difference. The rules for them are kind of dry, all right? As much as my bad jokes and silly sense of humor, I try to spice things up. Honestly, it's a little bit dry. But try to go through it. The examples, I think, are not that bad once you see them in action, but sometimes getting to it can be a little bit weird. So this last big section here is going to be on sig figs and how to use them. When you make a measurement, you always have some numbers which you know very accurately, and you have a last digit which is going to have some uncertainty. So in the last example with the volume, it's definitely more than 17 milliliters, definitely less than 18. So 17 would be the known digits where we all agree on. But we should go more than that because it's more than 17, less than 18. So we go one more digit than we know for certain. And this is called the doubtful digit. And it's always that last digit. So that's why I was saying like 17.4, 17.5. The 0.4 or the 0.5, that would be your doubtful digit, all right? And you go one more spot than you have the lines for. So on that picture, they're at 17, 18, whole number increments. You go one more decimal than you have the lines for. So those lines were whole numbers, 15, 16, 17, 18. That means the doubtful digit, one more decimal, so 0.1 milliliters. So on that last example, that's why I started with 17.4, 17.5, you could guesstimate or have a doubtful digit of 0.1 milliliters. One more line than you have the measurements for. Everybody knows in science that that one's going to be a little uncertain. And if we all went around here and you all wrote down what you thought the number was, you're going to see some variance. Some people will think it's 17.4, 17.6, 17.5, and that's okay. It's human nature to make your best guess at that digit, and everybody's going to have a little bit of difference. So that's why there's some uncertainty, some plus or minus in that one. It's a built-in part of the sig fig system. The total number of significant figures means you include the doubtful digit and everything that comes before. So on that last graduated cylinder, if we called it 17.5 milliliters, that would be a 3 sig fig number. The 1 and the 7 are the ones we feel really good about, and that last one, the 0.5, would be the doubtful one. We're not quite as clear on that one. It's got some uncertainty in it. Now, if you have a number then, like 65.07 grams, that would be a 4 sig fig number. The 6, the 5, and the 0, the scientists felt really good about when they measured it. But the 7 is the doubtful one, all right? They made their best guess, or even the electronics made their best guess as to what that number is. So the 7, the last digit, that's the doubtful digit. You'll see when we do the density lab, that last digit goes up and down. Like you'll stomp your boots, in my case, or whatever you're wearing. You'll blow on it weird. It goes up and down a little bit. Even electronics have an uncertainty with that last digit, and that's totally normal, all right? So if you see a number, 65.07, the last one is going to be the uncertain doubtful digit. Depending on your experiment, the doubtful digit can be quite different. So here it was 2 decimals to the right, the 100th spot. Here it's quite a gazillion, nice job. It's 5 digits to the right of the decimal, right there. The 8 is the doubtful digit. Notice here these 2 numbers. It's better as a chemist if you can get these kind of numbers. That's got a lot more significant figures in it. You have stuff which has a lot more accuracy, but you always will have a doubtful digit, that last one. It just depends on where you are. Questions? Okay. So 4 sig figs, the 7 is the doubtful digit. This one has 7 sig figs, and again, the last one, in this case the 8, is the doubtful digit. So doubtful digit can be anywhere in the number line. Okay, now, I apologize. These are really boring. Most of the time in sig figs, the non-zero numbers are no problem because those count. It's the lame zeros, which are usually the troublesome ones. So zeros can be in different places within a number, and I'm going to try and give you some examples here of when to tell if the zero counts or when it's just a placeholder. Placeholders are important. If I have 1 donut versus 10 donuts, there's a difference, all right? 1 and 10 are off by a factor of 10. But we need that 0 to share that it's 10 and not 1. Or you can imagine 100 versus 10. So sometimes zeros just tell you where you are on the number line. Are you at 10,000 donuts, or do you only have a tenth of a donut? All right? All these things you need zeros for. And so zeros don't always count when it comes to sig figs. But we need them to know if you have 10,000 donuts or only 0.01 donuts. So bear with me here. Zeros in the middle of non-zero numbers, always significant. So 69.08 would be a 4 sig fig number because the 0 is in between non-zeros. There's a 9 on the left and an 8 on the right. That 0 counts. All right, so that would be a 4 sig fig number. The 8 is the doubtful digit. If, though, the zeros are at the beginning of a number, like this one right here, this one, those zeros are just placeholders. We need to know that this number is 0.0089 and not 8900, 8,900 number. Or we need to know it's not 8.9. So these zeros, the 000, those there are just placeholders. They're not significant. What would be this number in scientific notation? 8.9 times 10 to the 1, 2, 3 times 10 to the minus 3. And the reason I bring this up is because if you're cool with scientific notation almost automatically pulls your zeros right out. We can write this without any zeros at all by writing 8.9 times 10 to the minus 3, all right? The 0, 0, 0 at the beginning, they all go away. Scientific notation can be really cool for sig figs. We'll talk about that more here in a little bit. If the 0 is after a non-zero, but after a dot, it counts, which is weird. If you have 2.50 milliliters, you could have 2.49, 2.51, you could have 2.50. So this is an example of when 0 counts. We have to have a way to show that this last position is a significant number. So again, you can think of this as being somewhere between 2.49 and 2.51, and the 0 is the doubtful digit. So again, 0 is after the decimal and after a non-zero number. I'm sure that's as clear as mud. But anyway, hopefully you can see here like why that can be important. If the 0 is after a non-zero but before a decimal, it doesn't count unless you have a dot. And earlier on, I showed a temperature. I think it was 310 Kelvin, and I put a dot next to it. That's the scientist's way to say that that 0 is a number that counts. So let's talk about 1500 versus 1500 dot. This number right here, 1500, has a doubtful digit plus or minus 100. The 5 is the last doubtful digit. So this would be a measurement where you had somewhere between 1400 and 1600. And maybe that's a really good value. But this has even higher precision. 1500 with a dot means that this 0 is significant. That's the doubtful digit. This would be somewhere between 1499 and 1501. So there's a lot smaller precision. Like you know this number to a lot more than you do this one right here. This is why the nature of the experiment is so bloody important when it comes to chemistry, all right? If you're doing kind of a rough job, 1500 without a dot is fine. you've got some number between 1400 and 1600. On the other hand, if you've got a good setup, 1500 with a dot would be great, because then you have somewhere between 1499 and 1501, that doubtful digit. A much smaller uncertainty here than you have over there. Sometimes in chemistry, you have exact conversions. Every time you go to the bank and you give them $1, they'll give you 4 quarters back 100% of the time. If you know of a bank that's different, let me know. But anyway, all the time 4 quarters equals $1. 60 seconds always equals 1 minute. 100 centimeters equals a meter. These are examples of what they call definitions. And those guys you don't have to worry about sig figs with. I will always tell you if a conversion is exact definition or not. It can be a little weird at first, but these guys you don't have to worry about sig figs. If you look at 60 seconds per 1 minute, this isn't 60 dot seconds, this is 60. So this would be a 1 sig fig number on the top, and 1 is 1 sig fig on the bottom. If you had like 4,200 seconds you wanted to convert to minutes, this would mess you up. So these exact conversions are immune to sig figs. And finally, I just want to say, this is stuff you gotta have some experience with. Just practice. I've got lots of examples and stuff in notes and sample problem sets, sample quizzes. The more you practice this, the better it gets. I'm gonna go through some examples now that hopefully will make this a little bit less crazy too. Are there any questions at this point? Okay, so here are 4 values, all right? All 4 have the same number of sig figs, true or false. This first number is 1,000 with the dot at the end. What does the dot tell you?
The zeros are significant.
The zeros are significant, well done. Normally 1,000 without a dot would be just 1 sig fig, but with that dot there, that means that all the zeros are significant. This number you can think about as between 999 and 1,001. So you bet this is a 4 sig fig number. How many sig figs in 9.730? Zeros that are after the decimal and after a non-zero number count. So this is actually a 4 sig fig number here as well. This one would be 9.729 to 9.731. This is also a 4 sig fig number right here. This one's a little funkier, but remember these have a lot of zeros at the front, and the zeros at the front can usually be expressed in scientific notation. So those zeros do not count. But this 0 is like this one up here, it's after the decimal and after a non-zero number. So believe it or not, this number right here also is 4 sig figs. We could write this number as 4.270 times 10 to the minus 3. And that would be a way to kind of cut down on the ambiguity a little bit. And then finally, this one right here, the zeros at the end only count if there's a dot. And this one does not have a dot. So that means that these 2 zeros are just placeholders. You could write this one as 2.998 times 10 to the 5th, and those zeros would go away. What that means though is that this is another 4 sig fig number. So the answer here is true. All of those numbers have 4 sig figs. They look quite different because of the placeholders, like these placeholders and those placeholders, but they are all significant. And watch for the dots, all right? In my world, that's a big thing. It's not a typo. If you think it might be a typo, you are always welcome to ask me. All right, scientific notation, pretty awesome. We're gonna talk more about this on Wednesday when we go through the recitation, but in a scientific notation number, and you've probably seen this before, just make sure, it's always written as a number between 1 and 10, and then times 10 raised to a power. So 215, if we wanted to write that as a power, we would first of all write it as a number between 1 and 10, so we would move the decimal over twice to make it 2.15. And if you move the decimal to the left, you make it a positive number, so we moved it 2 spaces to the left. That would be 10 to the positive 2. 2.15 times 10 to the second is the same number. So this is if you have a number larger than 1, but you can also have numbers that are smaller than 1. So if you wanted to convert this funky number into a power of 10, all right, you would write it 1.56, and you move it over, in this case, to the right 8 points. If you move it to the right, it gets a negative sign. That doesn't mean it's a negative number, it just means it's a really small number. And of course, you can go the opposite way to turn scientific notation into a regular one. Now, I'm going to assume that a lot of you have seen this before. We are going to talk more about scientific notation on Wednesday, but the number one thing I want to leave you with is that your calculator should be good at converting between regular and scientific notation back to regular. And that's going to be something we're going to hardcore focus on Wednesday, because that will help you. We're going to have really big numbers and really small numbers, and going between the two can be a really useful thing in this class. If you know how to do it on your calculator, you're good to go. If you won't, I'll make sure by Wednesday you will be good to go. Rounding, it can be important because you only want to report the number of sig figs that you actually use. Because sometimes the experiments themselves will be kind of cheesy and you'll get cheesy results. On the other side, if you have really good experiments, then you'll get good measurements. So rounding is an important part of chemistry. And there's different ways to round depending on if you're multiplying and dividing, which is what we'll use most of the time, or if you're adding and subtracting, which we'll use occasionally. Now, multiplying and dividing, people are usually pretty good at. The number of sig figs in must equal the number of sig figs out, and you use the smaller number of sig figs. So here's an example. Maybe in my car, I drove and used 11.70 gallons of gas, and I drove 278 miles. So in the calculator, if I put 278 divided by 11.70, I get a number that goes on for quite a ways. But notice here the number of sig figs. I had 3 sig figs in the miles and 4 sig figs in the volume. 3 sig figs is smaller than 4 sig figs. That's why the best answer here, 3 significant figures. I don't have the 4th sig fig here to make this a better number. So I need to cut this one off at 3 sig figs. So 23.7, I cut it off after that. And we're going to see if the number is between 5 and 9, you make it bigger. So 23.7 becomes 27.8. Now, if I would have done a better job and maybe looked at my odometer better, maybe I used 278.0 miles or something like that. Then I would have a 4th sig fig, and I could call it 23.76, 4 sig figs in my answer. But the way this problem is set up, I can only refer to it as 3 sig figs. Any questions on that? People usually do pretty well on multiplying and dividing. All right, that's pretty straightforward. The one thing that I do see a lot of times though is when people add and subtract, because it's a little weird. We talked about the doubtful digit, how the doubtful digit is the last number on this. Let's say that we have measurements of 3.18 liters and we want to add 0.01315 liters to it. All right, you put all these numbers together and you get 3.19315. But the problem in chemistry is that we don't know these 3 numbers right here. We were only given 3.18 liters. We weren't told what these were. Like maybe this is a 4, maybe it's a 1, maybe it's a 7, right? We don't know any of these numbers. So how can you add numbers together when you don't know what you start with? That's the problem we run into in chemistry. So in chemistry, you always cut it off at the largest doubtful digit. 8 is 2 to the right of the decimal, and 5 here is like 1, 2, 3, 4. It's 5 to the right of the decimal. The bigger one is to the left. That's why I wrote this little line right here. I want to cut it off at 3.19 liters. because that's as far as this measurement goes. I just don't know those numbers to have any confidence in the value we report. Again, this is all experimental-based chemistry, right? Everything we do is experimental. So if we don't have a good number, then it would be awkward to report any further than it is right now. So again, when it comes to adding and subtracting, you always cut it off at the largest doubtful digit. And that's where it's really important to know. And this is for both adding and subtracting. Questions? Okay. Once you have the number, you need to be able to round it off. And again, the punchline is that the first number you drop, if it's between 5 and 9, round up. But if the first number you drop is between 0 and 4, leave it alone. And that's basically what that says right there. So let's say we have a number, we calculate 2.4271, and we want to round this number to 2 sig figs. Well, 2 is the first one, 4 is the second one. We cut it off right here. But you want to look at the first digit you cut. This is a 2 between 0 and 4, so we just leave it alone, 2.4. On the other hand, here's 4.5816. We want to round this to 2 sig figs. We keep the 4, we keep the 5, cut it off after the 5, but we look at that first digit, and that's an 8. If that number is between 5 and 9, you round up. So instead of calling it 4.5, we're going to call it 4.6, all right? The textbook uses some weird things about when you round the 5, you ignore that. 5 to 9, round up, like this one. 0 to 4, leave it alone, like this one. Most of the time I like our textbook, but this is one place where it makes me mad. But anyway, I had lots of therapy and I'm okay now. No, seriously, I'm over it now, but it was a problem for a while. Sorry, questions? Yeah.
So if it's 2.5, you just leave it?
Yes, if it's 2.5 and you wanted to round it to 1 sig fig, the 5 would be the first you cut, and between 5 and 9 you would round up. So that would be 3 in that case. Like 2.5 would become 3 to 1 sig fig. But if it was 2.499999, 4 is the first one you cut, you would leave that one then at 2. Is that cool? Good. Other questions? We're going to do lots of examples of this, by the way. Let's round this problem to 3 significant figures. This will be the last thing we do here. All right? So first of all, we have to think, oh goodness, here's a bunch of zeros in front, and those zeros are just placeholders. All right? The 0, 0, 0, they're just telling you where the number starts on the number line. So these are not significant. The 3 right there is the first significant value. And to 3 sig figs, it would be 3, 0, 3. We'd leave those, but then we'd put a line, if you will, right after the second 3. Now 5 is the first, like you just asked, that's a good question. 5 is the first number we're going to drop. 5 is between 5 and 9. So do we round up this 3 to a 4, or do we leave it as a 3? You bet. We're going to round it up to a 4. All right. So 30350 would become 304 or 0.00304. And again, I don't care what that stupid book says in this part. If it's a 5 to 9, round up. 0 to 4, leave it alone. Good to go. Any questions on this? All right. Really glad to have you all here live with me. I really appreciate it. For Wednesday morning, we'll meet here at 8 a.m. Bring your calculator with you if you can, and bring a printed copy of the 8 bottles lab. We'll be good to go. We'll actually do a lab. We'll talk more about sig figs and stuff like that at that time. Awesome having you here. Email me your questions anytime. Have a great day.